Hi guys, welcome to today's video. I'm Atray and I'm a faculty of Science, Physics and Chemistry specially at Cosmic Essence Education. So today we'll be discussing the difference between electric field and electric flux, because I know a lot of you have issues with understanding the difference between these, and we'll be discussing and deep diving into these topics today. So let's get started, but before that, do share the video and do like and comment your queries below so that we can make better videos like this, as well as get your friends to understand these concepts better so that you can discuss these better with them. So let's get started for today's video. So the first thing that we'll start with is understand what electric field is, right? So an electric field is simply an area, a space which has force per unit charge, right? So we define an electric field as force per unit charge in an area by a charge or system of charges. Right, because a field can be created by a single charge or maybe by multiple charges put together. So that is what an electric field is. What does this mean? Suppose I have a charge Q right here in the middle of this board, right? And then I get a test charge. This is called a source charge because this is the charge that is creating the electric field that we are trying to understand. And then I bring a test charge, say any test charge, right? I bring it over here, and this test charge is very small, right? So the force on this test charge by Q is how much? It will be given by, if this is the distance r between them, the force here will be given by K Q into test charge. Let's call the test charge capital Q upon r square, because this is what we get from Coulomb's law, right? So this is simple application of Coulomb's law. We're trying to understand the force by this source charge on this test charge, and this is what it comes out as, right? And the direction of force is outwards, considering that the test charge is also a positive charge. Okay, so once we understand this is the force applied by small this source charge on the test charge. Now if I wanted a unit charge over here, right now the charge has a magnitude of capital Q, that is what we are denoting it as. But what if I wanted to know what is the force applied by source charge over here at this distance on a unit charge? Unit charge essentially means that the magnitude of the charge will be 1, right? 1 unit. It can be anything. It can be coulomb, it can be microcoulombs, whatever the unit that we choose for charges. So in that case, what will I do? I will divide this force by Q. I would divide this force by Q, and now I will get KQ r square, and this is the force applied by the source charge at this distance on a unit charge, and this is what we define as an electric field at this distance, right? So this is what electric field is. Now as you can see from here that there is no aspect of this test charge, right? Test charge, because it is unit, so I can just write 1 over here and it works. It's the same as KQ upon r square, right? So this becomes my magnitude of electric field at this distance r. And again, this r, if I make a circle around here, it will be the electric field around the circle on each point of the circle will be the same. So electric field in this case, because this is a point charge, it will be same on every point from that source charge at a particular distance, right? So this is what electric field is about. It is not anything else, and we'll come to what electric flux is, my bad, but it's simply the force on a unit charge in a given area by either a single source charge or a system of charges, right? So once you've understood this, what electric field is by a single charge, let's now see what happens in the case of a system of charges. In the case of a system of charges, suppose I have three charges like this: Q1, Q2, Q3, right? This is a system of charge, and this is where my test charge capital Q is. Again, to first figure out what is the force over here, what do I have to do? I simply have to add up all the forces by each of the individual charges at this point. What are the individual forces at this point? If I take this is individual force like this is another individual force by Q1, and by Q2 this is another individual force. So I can see three different forces, and then what do? I essentially do a vector addition of all of these three vectors at this point. So at this point, if I do the vector addition, it will come out very simply as, let me remove this and make it again. It will be simply in this direction, forward direction, considering they are in a triangle, and this will essentially be addition of all of this, right? So angles and whatnot will matter, so all of that needs to be dependent on the theta and the angles that are there, but we can apply the superposition principle on Coulomb's law to get the vector addition of the force at this point by the three charges here, and they will come out as a single vector like this, right? Because we can always find the sum of vectors. Now what do I do after this? Whatever this comes in, suppose this is K, whatever this is, let's just call it force. This force divided by this charge will give me the force on a unit charge at this point, right? Because right now this force is applicable on the magnitude of charge Q, capital Q, but if I divide this force by capital Q, this will give me the force on a unit charge by this system of charges, which is exactly what my electric field is, right? This is how I define electric field as. So this is what electric field is all about, right? With a system of charges and a single charge. But now, why is this so important? Why is this so important? It's important because in electrostatics, when we are just dealing with static charges which are not moving, it does not matter, right? Because it's the same thing. We just have to add them together and do vector addition and all of those things. So it does not matter. But it is extremely useful to understand this concept of field when we are talking about electromagnetic induction or electromagnetism in general. What happens there is, suppose I have a charge here and I have, say, something, let's just call it, it's just a measurement tool, right? So right now this Q is applying a force F initially. Let's call it Fi, right? Now when I change this, or when I add another Q to this becomes 2Q. Okay, it might seem abstract, but I can add another charge at the right exact same point, and I will have 2Q over here. With 2Q over here, what's now going to happen is, and it happened very quickly, the initial Fi will remain the same, but then as my another charge gets added up, the new force will have to travel through to this point and give me another force F final. Right? Why does it have to travel through? Because this change can only travel with the speed of light c. Right? So there is a limit to the speed that this change can travel. It's not instantaneous. There is always a gap in time. And so to showcase that gap in time, the field concept is a beautiful concept to explain it, right? So by this change at the charge level, I am changing the force experienced by this receptor or this tool over here, because the velocity through which it can reach, the effect can reach the receptor, has a fixed magnitude, right? So this time lag between changing from Fi to Ff, this needed to be explained in the terms of electromagnetic induction and electromagnetism in general, and that's why the concept of field was given by Faraday. So that's what field is about, right? And that's why it's such a really cool concept. Okay, now once we've understood field, let's quickly go through what is electric flux, because this is where confusions happen. Electric flux is quite a simple concept again, but a little confusing. What happens is, when I take an object, right? Suppose I take a cylinder. Suppose I take a cylinder like this. Now through the cylinder, I have charges passing through, or there is electric field existing in this cylinder. Let's say the direction of electric field is this way. Right? When my direction of electric field is this way, in this cylinder, I want to figure out that if I take a part of this cylinder, part of an area of this cylinder, I want to know what is the strength of electric field in this area, right? Now flux in common terminology is used for fluids which are passing through any body, right? In that notion we are using flux, but here what we are imagining, this is what visualization is about, because we can't really see and it does not really happen, but we are visualizing that electric field is passing through this cylinder, and when it passes through the cylinder, I have cut a small square shape in the middle, and then I want to figure out that from this square shape how much fluid is passing through. That means, how will I figure it out? I will need to figure out how much fluid is passing through this square shape. I will of course need the area. I will of course need the area by S, delta S, right? Delta S, because it's a part. So this is the area, and of course the magnitude of the velocity that is passing through. Now obviously, because we are talking about electric field does not have velocity, but what it does have is the strength of electric field at this point, right, in this area. So I will multiply this with electric field, and this is what flux is, which we denote by phi. So again, what is happening over here? We are imagining that electric field is a liquid which is passing through an area, which is passing through a cylinder, and in that cylinder we have taken a small area, small part of the area, and we want to figure out how much fluid is passing through this small area in a second or in a unit time. And so we are triangulating that by, first I need to know what is the area through which the fluid will be passing through, and of course what is the speed which with the fluid will be passing through. These are the two things I require, and then I get this. But of course, because electric field does not have velocity, we will use the intensity of the electric field at this point. Now here this is direct multiplication because both of these are at 90 degree to each other. That means direction of electric field and the area, the piece of area are at 90 degree with each other. But what if the area turned like this, right? So earlier it was like this, completely in alignment, and then it turned like this. What would happen? What would happen is the amount of flux or amount of electric field lines or amount of liquid that will be passing through my hand now will reduce. Why? Because the area has reduced in the direction of the flow, right? The area has reduced in the direction of the flow, and that's why in that case I will have to multiply it with cos theta. I will have to multiply it with cos theta, where theta is angle between the electric field vector and n cap vector, n cap area vector. The electric field vector, which is this arrow, and the n cap area vector. N cap area vector is the normal to the area vector. So in the initial case this was the n cap, but now as my hand turned a little bit, the n cap has changed, and so there is now an angle between these two vectors, and so that is the theta that we will be using here. That's why this is E dot delta S, which means it's a dot product between electric field and area. Okay, so this is what electric flux is. That means, in simple terms, what we are talking about is essentially the area is the electric field and area need to be in the same direction to have the maximum flux, and if they are at 90 degree to each other, that is if they are at 90 degree to each other, then there will be zero flux passing through. Okay, so that is what the difference between electric flux and electric field is, which is electric field is just the force per unit charge given by a single charge or a system of charges, and flux is the amount of electric field in a given area. It's the amount of electric field or the strength of electric field in a given area, right? That is what flux is all about. So I hope the difference is clear to you now. So thank you for watching this video. I hope you liked what I shared today about electric field and electric flux, and you are clear on the difference between them. If you're not, do drop in a question in the comments below, and I will try to answer it as soon as possible, or maybe in the next video that I put up. Do like and share this video with your friends so that you can enjoy discussions with them in a much clearer way. Also, do not forget to subscribe and hit that bell icon so that you know when we are putting up the next videos. So thank you for joining in, and I'll see you in the next video.